Okay, in this question, a ring of radius r is placed such that it lies in vertical plane. The ring is fixed. The bead of mass m is constrained to move along the ring without any friction. One end of the spring is connected with the mass m and the other end is rigidly fixed with the topmost point of the ring. Initially, the spring is unstretched and the bead is at a vertical distance r from the lowermost point of the ring. The bead is now released from rest. Okay, so here like the spring is unstretched. Okay, so that length of the spring we can say easily that it is nothing but root 2r. Okay, when that bead comes to the lowermost point, right, so that time that the spring will be stretched, okay, and the total length of the spring will become 2r, which is the diameter of the ring. So we can see the stretch in the spring will be equal to, so the length of the spring will be 2r and this is the initial original length. So the stretch will be in the spring will be h is equal to, we can say 2 minus root 2r, right? So that is the stretch. Okay, now the part A, what should be the value of spring constant k such that the bead is just able to reach bottom of the ring? So from this point to this point we'll apply work energy theorem. So let's call this point A, this call point B. So from A to B, applying work energy theorem. So from A to B we can say the work done by all the forces equal to changing energy, that is the work energy theorem. Now the forces those are acting on the bead from A to B is the gravity, so work done by gravity, and one force is spring force because spring is stretched, so work done by spring. There is no friction and that's it, is equal to delta K. Now initially A point that is released and B point we are saying that it just reached at B point, so delta K is equal to 0. So here we have work done by gravity plus work done by spring equal to 0. Work done by gravity will be simply like mg into r, because the vertical displacement is r only, and work done by spring will be like half k h square, and h is 2 minus root 2 r square is equal to 0. So from here we will calculate the value of k. So mg r is equal to k by 2, and if we solve this one, like it will be like 4 plus 2 minus 4 root 2 into r square. So k is equal to 2 mg divided by, and it's coming 6 minus 4 root 2. So if we take 2 common, so it will be like 3 minus 2 root 2, and it's cancelled. So the k value is coming as mg upon 3 minus 2 root 2. Now that is the value of k. Okay, so that we have solved part A. Now come to the part B. So in the part B we need to calculate the tangential centimeter acceleration of the bead at initial and the bottommost point of the position for the same value of spring point. Okay, so now it is very simple. At A point it is just released, right? So at A point it is just released, so speed is 0, so centripetal acceleration is 0, and the tangential acceleration, and the spring is not applying any force, so there is no acceleration from the spring side, only gravity side there is an acceleration g, and that is tangential, so at will be g. And at B point, which is the bottommost point, so obviously that tangential acceleration is 0 because there is no acceleration in horizontal direction, and the centripetal acceleration is also 0 because the speed is 0 with this value k, right? Because we calculated k value with this condition, k is just able to reach at the bottom, so we assume that final speed at B point is 0, so their acceleration, centripetal acceleration is also 0. So these are the values of tangential and centripetal acceleration at A and B point. That's it. Thank you.